Today we're going to look at rigid and non-rigid transformations and how they relate specifically with triangles. So our lesson goals are to review what rigid transformations are and how it leads to congruence, and then define dilation, scale factor, and center of dilation. We'll do 2 examples of how to dilate and 2 examples of finding the scale factor. And then we're going to define similarity and do 2 examples of that. So let's review the congruence, which comes from rigid transformations. Rigid transformations mean that we're not changing the shape at all. We're just moving it around. So we have a translation, which is just a slide. So left, right, up, and down. Okay. So we have object to image. Image is the new shape after it's been transformed. A rotation is just like a turn, right? So we can rotate it about a point on the shape or around a separate point. And then a reflection, which is like a flip. So here's our object to our image. Right, so we started here and we ended here. And we flip about a line. We flip across a line. And all of these keep congruence. When we slide, rotate, or reflect, we're not changing the shape at all. We're just changing where it is. So 2 shapes are congruent, and this is our sign for congruent. Right? So they're congruent. It's a squiggly with an equal sign. If their angles are congruent, and their sides are congruent. So basically, they're the exact same shape, right? So here are our angles. Our triangles have 3, and they are marked congruent with congruent marks here. So the angle with 1 mark is congruent to the angle with 1 mark. The angle with 2 marks is congruent to the angle with 2 marks, and the angle with 3 marks is congruent to the angle with 3 marks. So all 3 of our angles are congruent, and then our sides are marked with congruence as well. So 1 tick mark, 1 congruent mark, shows that it matches with the side with 1 congruent mark. 2 to 2, 3 to 3. So we could actually use rigid transformations to match triangle ABC to triangle EDF. Okay? So if we want to match this angle to this angle and this second angle to this second angle, would we need to rotate or reflect? Yeah, we would actually need to reflect this, right? Because these are on opposite sides. If we rotate it, this second one is never going to get to the other side of this. So we are going to reflect this, and then we could translate it, and it would match. B would match to E, A would match to D, and C would match to F. Okay, but we really want to focus on non-rigid transformations, specifically a dilation. A dilation is when you are enlarging or reducing a figure. So enlarging means we're making it bigger. Reducing means we make it smaller. Okay? So when you have a dilation, you have what's called a scale factor, which we use K to represent. And that is the ratio of corresponding sides. Basically, it's the number that you're going to multiply by to make bigger or smaller. Okay? If K, your scale factor, is greater than 1, so like multiply by 2, or times 3, or times 10, even times 1.5. If it's bigger than 1, your shape is going to be an enlargement. Right? We're going to get bigger. If it's between 0 and 1, so I'm talking about less than 1 but not negative, so like times 0.5, times 1/4, times 0.001. Anything that is smaller than 1 is going to make your figure get smaller. Right? It'll be a reduction. And your center of dilation is the point where the dilation is expanded from. Okay, so that's just how we do our calculations. Let's do a couple examples of how to dilate a figure with the center at the origin. We're going to focus only on the center at the origin for this lesson. Okay, so in order to dilate this figure, we just need to multiply the coordinate points by the scale factor K. So in our problem it says dilate triangle ABC if K is equal to 1/2. So if my scale factor is 1/2, should I expect an image that is larger or smaller? That 1/2 is less than 1, so it's going to get smaller, right? With a center of dilation at 0, 0. So what we're going to do is we actually need to take each of these coordinate points, okay, and reduce them by half. So this first point A, it's at the coordinate point -4, 0. So all I need to do is multiply by a half. Okay, and that's going to give us the point, we call it A prime. Let me fix that. All right, and it's just an apostrophe to show us that it's the new image. So A prime. I'll write that over here. So if you see this little apostrophe, it's called prime. And it represents the new image. Okay, so I'm just going to multiply -4 times a half, which is going to be -2. 0 times a half is 0. So it tells me where my new point is, -2, 0. Anytime you do this, make sure you label the point. It's helpful to do it right after so you don't lose track. Okay, now I'm going to do B and C. So B is at the coordinate point 0, 4. I need to multiply by a half because that's my scale factor. So what would B prime be? It would be 0, 2, which is right here, B prime. And then our last one, C. C is at -4, 4. And if I multiply each of those by 1/2, C prime would then be -4 times 1/2, which is -2, and 4 times a half, which is +2. So that's going to be at -2, +2. So we should see that the shape should look the same. We didn't change anything else in the triangle except for how big or small it is. So it should look like the same triangle except half smaller. Okay, and I think we've successfully done that here. Let's do one more example. Dilate triangle ABC if K is equal to 2. So if my scale factor is equal to 2, would this be an enlargement or a reduction? This would be an enlargement. We're getting bigger because our number is greater than 2. It's like doubling in size. Okay? So it's going to be the same idea here. We're going to take the coordinate points and multiply by 2. So we're going to start with A, which is at the coordinate point -5, 2. I need to multiply both by 2, and I get my A prime, which is -10, 4. And I did not make my grid big enough, but we can estimate here. So -10, and then up to 4 would be somewhere in this area, A prime. Okay, now let's do B. B is at the point -3, 4. So -3, 4. If I multiply everything by 2, B prime would be what? -6, 8. Very good. So -6, +8, which I did not make big enough again. We're probably up here. So my drawing is going to be a little bit off. And then our last one here, C, was at -2, 0 on my graph. So now C prime, if I multiply everything by 2, because that is my scale factor, K, that would be -4, 0, which would be right here. So if I connect it, assuming that I estimated correctly over here, it should look like the same triangle, just bigger. All right, it doubled in size. Okay, so that's how you use a scale factor. Now can we find a scale factor if we have a dilated figure? How to find the scale factor? Well, I'm actually just going to divide my numbers, okay? And I put divide the coordinates here. There's actually a couple different methods I'm going to show you. All right, I just need to know what did I multiply by in order to get my new shape. Okay, so let's look at this first one. It says find the scale factor. Now, do you think I went small to big, or did we go big to small? We went small to big here because this is point A, this is point A prime, okay? So there should always be something in my problem to tell me which direction I went, okay? So if I'm getting bigger, should my scale factor be greater than 1 or less than 1? Yeah, we want to be greater than 1, right? So in this, if I try to look at my coordinate points, right, we expect it to change. This is the point -2, 1, and it should match up here to -1, 2. What would I have multiplied by? Well, it works a little differently for this one because my center of dilation is not at the origin, all right? If I draw the lines that connect these together, kind of like a shadow, we can see that our center is not at the origin. So we can't just look at the coordinate points for this one, but we can look at the size of our triangle, okay? So I'm going to look at my side lengths. This was a length of 1. This one was a length of 2. I'm not going to worry about this one right now because I would have to use Pythagorean theorem there, okay? Let's look at this one. Our BC prime was a length of 2, and our AB prime was a length of 4. So we went from a side 1 to a side of 2, and a side of 2 to a side 4. So what do you think the scale factor is? Yeah, it's times 2. Our K equals 2, which is greater than 1, which we expected since we got larger. Okay? So now if we look at this one, if you're centered at the origin, you can look at your coordinate points. And if I connect my shapes together, I can see my center of dilation was at the origin, so I can just use my coordinate points, okay? All right, so I need to know, I went from an x value of -5 to an x value of maybe -7.5. That one's a little tricky, isn't it? Let's look at another one, see if it's easier. This one went from -4 to -6. So I'm just looking at just the x because the same thing happened to the x as it did to the y. So you can just look at one at a time. So this went from a point -4, -3 to -6, possibly -4.5, right? We don't know 100%. And then let's check our c and our n. Okay? This was the point 2, -2 to the point 3, -3. Okay? I forgot to see which direction we went. Are we getting bigger or smaller here? Well, if we look in our problem, it says find the scale factor from triangle ABC to triangle LMN. So we're starting at ABC and we're going to LMN. So that means we are getting bigger here. Okay, so we need to know what do we need to multiply these coordinates by to get these new coordinates at LMN. If you're not sure, you can just divide them. I'm going to stick with the whole numbers because I'm not sure if the decimals are accurate. All right, if we're just looking at a graph, it's hard to tell what the decimal is. So here I can just take -6 divided by -4. And I'm just going to reduce that. Negative over negative is positive. 6 over 4 can reduce to 3/2. Now let's check to make sure that makes sense over here. We went from a 2 to a 3. Well, if I divide them, 3 divided by 2 is 3/2. So what that means is, in order to get to point A to L, I would have to take 3/2 and multiply it to the -4 and to the 3. Let's see if it gets us the right numbers. This is a way to check yourself. So I am just taking what I think is my scale factor, multiplying it to my coordinate here to make sure it makes sense. Well, -4 times 3 over 2 is -12 over 2, which is -6. That lines up. Let's try again. -3 times 3 over 2 is -9 over 2. And if you put that in your calculator or do your mental math, that is -4.5, which makes sense. So all this work was just to confirm that our scale factor is 3 over 2. We expect it to get larger. 3 over 2 is greater than 1. I think we have the right number. Okay, when you have dilations, it actually creates similar figures. Before we looked at congruent figures, dilations actually create similar figures because we're actually changing something about the shape, right? Two figures are similar, and this is our symbol for similar, right? It's kind of like just a curly thing like that. If their angles are congruent, and their sides are proportional. Okay, and what that means is that they were all growing at the same rate, right? And that could be getting bigger or getting smaller. But it was the same rate. Each side was changing at the same rate. And I'll show you how we can confirm that. So when you're looking at similar figures, we are talking about same shape but different size, right? So a dilation doesn't change the way the triangle looks, but it changes if it's bigger or smaller. So here's an example of two similar triangles. If we notice, all the angles are congruent. So congruent 1 mark to 1 mark, 2 marks to 2 marks, 3 marks to 3 marks. It's telling us that all 3 of our angles are congruent. So the first part of our definition is good. And that's the same as congruent triangles, right? But if I want similar triangles, I need proportional sides, not congruent sides, okay? So I've got to look here. Our smallest side should line up with our smallest side, right? This is between angle with 1 mark and 2 marks. This is between 1 mark and 2 mark. So these sides should match up. What do I need to multiply 4 by to get to 28? Yeah, 4 times 7 is 28. So that means that my scale factor should be 7. But we need to check. Does it work for all of our sides? 6 times 7 is 42. 5 times 7 is 35. So every single side was multiplied by the same number, which means that we have the same scale factor of 7, which makes our sides proportional. Okay, that's what it means to be proportional. Everything was multiplied by the same thing. Now remember though, it doesn't change your angles. Your angles are congruent. Okay, so we can actually prove two figures are similar by just using transformations. If they're similar, then we should be able to use rigid and non-rigid transformations to prove that. So, if a series of transformations can map one figure onto another, then the figures are similar. Map means that they can line up exactly. So let's look at example 1. So we have this triangle, this 3, 4, 5 triangle, and it says that this first angle here is congruent to this first angle here, but this is a 6, 8, 10 triangle. So we need to think, what transformations could we use to match this first triangle to the second triangle? Well, we would need to shift it over, right? So if I want to shift it over, which transformation is that? That would be a translation, and specifically here a translation right. We don't know how many units because we're not in a coordinate grid. Okay, if we translate it right, we would be on top of each other, but we wouldn't match. This one is smaller than this one. What transformation could we use to make them the same size? It'd be a dilation. Now let's check if dilation truly works. I need this 3 to match with the 6, this 4 to match with the 8, the 5 to match with the 10. So what could my scale factor be? We can multiply by 2. So here I have a translate right and dilate by scale factor of 2. I can multiply all my sides by 2 and end up with the triangle right over there. So that proved that we had congruent angles but proportional sides. Let's try one more time. Okay, so we have triangle ABC and triangle DEC. Can we make these match up? So, do you think we need to rotate the big triangle, or do we need to reflect the big triangle? So this is a little bit tricky one. These little arrows here tell us that our lines here are parallel. So I'm going to extend that so you can kind of see what's going on. We're going to review a couple things about parallel lines. Okay, if I have parallel lines with a line going through it, then we have some congruent angles. We have these two angles here in the center. I know they're congruent. They're called vertical angles. Vertical angles, okay? It's kind of like kissing angles is sometimes a term I've heard. And then with these parallel lines, we actually have another set of congruent angles. these two angles here are called alternate interior angles. So I know that they are congruent. And that's called alternate interior angles. So it looks like we have some sets of congruent angles, okay? And we actually have a second set of alternate interior angles here that I could mark as well. So that means that I need A to match up with E and B to match up with D. So a reflection would not work here. It would have to be a rotation. Imagine taking this, I'm going to rotate it around. So this one would rotate down here, this one would rotate up here. So the first transformation we need is a rotation. And that would be a rotation of 180 degrees clockwise is how we would say that. Okay? Now, is that enough? No, we're different sizes, right? So we actually need this to get smaller. So we need a dilation. Okay, let's figure out the scale factor. If we're going to rotate, then we have this 15 would match up with the 10, the 12 with the 8, the 9 with the 6. If you're not sure, it should be smallest to smallest, largest to largest. So smallest side on this triangle to smallest side on this triangle. Largest side on this triangle to largest side on this triangle. Okay? So I need to get from 15 to 10. What would I multiply by? If you remember from earlier, we can just divide them, right? So remember, you divide the second one by the first one. So I'm going to do 10 divided by 15, which would reduce, divide both by 5 to 2/3. Let's check the rest. We think that our dilation is 2/3. So that means if I multiply these by 2/3, I should get my two sides over here. 12 times 2/3 would give me 24/3, which is 8. So our 12 matches up with our 8. And then let's check our last side here. 9 times 2/3 is 18/3, which is 6. So we have confirmed that our scale factor, which I'm just going to shorthand with K, is 2/3, which makes sense because we need to get smaller. And that is our last example for today.